Electrostatic potential and capacitance exercises. Question 1. Two charges 5 into 10 power 8 minus 8 coulomb and minus 3 into 10 power minus 8 coulomb are located 16 centimeter apart. What point or points on the line joining the two charges is the electric potential 0? So here, the first case, we can take like this. We can take the total distance between two charges, Q1 and Q2 is T, and there is a point in between at a distance R from Q1. And the total potential at a point P must be 0. So in that case, we can take the potential at P due to Q1 and Q2 is 0. That is V1 plus V2 equal to 0. So V1 plus V2 is equal to 0. Then we can substitute the values of V1 and V2. So V1 formula is 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught Q1 divided by R plus 1 by 4 pi epsilon naught minus Q2. As per data, Q2 is negative, minus Q2 divided by D minus R. That must be equal to 0. So now, in such a situation, you can substitute the values, simplify, find the value of R. So in between the charges, at a distance R, the potential is 0. Now the same idea we can use to calculate another point, maybe outside. So in that case, again, the same method we need to follow. So we have to take a point outside, take that point at a distance x, and use the same formula. Q1 is at a distance p plus x, and Q2 is at a distance x. Substitute in the formula in the place of R and D minus R, and find the value of x. Like using that method, you can calculate the point outside Q1 and Q2. Okay. Now come to question 2. A regular hexagon of side 10 centimeter has a charge 5 coulomb. The diagram is given there. Charge Q is 5 into 10 power minus 6 coulomb. And side of the hexagon, it's a regular hexagon. So being a regular hexagon, the side is 10 centimeter. 10 centimeter. So that half of this diagonal also will be 10 centimeter. Therefore, we can conclude each charge is 10 centimeter from the center of the hexagon. And we need to calculate the total potential. Again, total potential V is equal to, we can use the same formula of potential. V is equal to, there are 6 charges, 6 into 1 by 4 pi epsilon naught, 6 into 1 by 4 pi epsilon naught, Q divided by R is the total potential at the center. Now, next question 3. Two charges, 2 microcoulomb and minus 2 microcoulomb, are placed at points A and B 6 centimeter apart. Okay, identify the equipotential surface of the system. What is the direction of electric field at every point on this surface? You can see here the charges are 2 microcoulomb and minus 2 microcoulomb. That means they are equal and opposite charges separated by a distance 6 centimeter, which means it is a dipole. So, being a dipole, we can see charge Q1 and charge Q2, both are equal and opposite charges. And at the midpoint, the potential is 0. You know, at the equatorial plane of a dipole, potential is 0. So in this particular surface, we can take a surface here. In this surface, the potential is 0 at every point. Therefore, at midpoint, the surface passing through the midpoint and perpendicular to the length of the dipole, having 0 potential at every point, therefore, this particular surface is an equipotential surface. Hence, in the properties of equipotential surface, we have studied the directional relation between equipotential surface and direction of electric field. And you know, the electric field is always perpendicular to the direction of equipotential, or perpendicular to equipotential surface. That is the answer to the second part. The electric field is always perpendicular to equipotential surface. Now, question 4. A spherical conductor of radius 12 centimeter. Radius of the conductor is given 12 centimeter. Charge is uniformly distributed. Total charge in the conductor is given. Now, question, what is the electric field inside the sphere? You know, inside the conductor, electric field is 0. Therefore, the answer to the first part is 0. Electric field is 0 inside the conductor. Now, second case, electric field just outside the sphere. So we can use the formula electric field E is equal to, assuming as a point charge, we can take 4 pi epsilon naught, 4 pi epsilon naught Q divided by R square, where R is the radius. Now, next part C, at a point 18 centimeter from the center of the sphere. So, at a point 18 centimeter, so E18 will be 1 by 4 pi epsilon naught. Again, we have to use the same formula. 1 by 4 pi epsilon naught Q divided by R square. And R will be 18 centimeter, which you need to convert into meter. So you will get the answer. Now, question 5. A parallel plate capacitor with the air between the plates has a capacitance 8 picofarad. 1 picofarad is 10 power minus 12 farad. What is a capacitance if the distance between the plates is reduced by half and the space between them is filled with a substance of dielectric constant 6? Okay, so the data is given. Dielectric constant 6. Now, capacitance formula we can take C is equal to parallel plate capacitance epsilon naught A by D. That we can take as air capacitance C naught. Now, C is equal to, what are the changes we obtained? We need to consider C is equal to, first of all, a dielectric slab is placed so that the capacitance becomes K times. Then epsilon naught A, distance between the plates is reduced by half becomes d by 2 is equal to 2 goes to numerator 2k into epsilon naught a by d, that is c naught, and value of k and c naught are given in the question, so that you can find the value of new capacitance. Now next, question 6. 3 capacitors, each of capacitance 9 picofarad, are connected in series. What is the total capacitance? Total capacitance, directly we can use the formula for series connection. You have 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now, what is the potential difference across each capacitor if the combination is connected to 120 volt supply? So, can do one thing. First, find the, we will get the effective capacitance, then find the value of charge in the capacitance. Q is equal to Cs into P. And you know, the charge in each capacitor will be same in a series combination. Therefore, now potential V1 you can calculate. V1 is equal to Q divided by C1. And use the same formula to find V2 and V3. V2 and V3. V2 and V3. Now, next, question 7. 3 capacitors of 2 picofarad, 3 picofarad and 4 picofarad are connected in parallel. What is the total capacitance? So direct calculation only. C parallel is equal to C1 plus C2 plus C3. Then determine the charge on each capacitor. So applied voltage is 100 volt. You know, in parallel combination, the voltage across each capacitor remains constant. Therefore, Q is equal to Q1 is equal to C1 into V. Find the value of Q1 and use the same formula to find the value of Q2 and Q3. Q2 and Q3. Now, next question 8. Again, area of the plate is given, distance between the plate is given, and you are asked to calculate capacitance of the capacitor. So capacitance C is equal to epsilon naught A by D. So direct calculation, epsilon naught A by D. If this capacitor is connected to 100 volt supply, what is the charge on each plate of the capacitor? Q is equal to CV. Then question 9. Explain what would happen if the capacitor in the previous question, a 3 millimeter thick mica sheet of dielectric constant 6 were inserted between the plates while the voltage supply remains connected after the supply was disconnected. So first of all, you have to see here mica sheet of 3 millimeter thick. D is also 3 millimeter in the previous question. That means what happens? The capacitance becomes C is equal to K C naught. That's the first two. Capacitance becomes K times. Now, next, we take case A. In case A, while the voltage supply remains connected. If voltage supply remained connected, then in case A, we have to take V is equal to V naught. That is, final voltage is equal to initial voltage. And if V is equal to V naught, then other quantities. What will happen? We have to see. Like a charge we can take. Charge here. Q naught is equal to C naught V naught. Now Q is equal to CV is equal to what happens to C? C becomes KC naught and V equal to V naught. Therefore, becomes K into C naught V naught. That means what happens to charge? The charge Q is equal to K into Q naught. The charge is increased by K times. And this method we can use again if you want to calculate energy, use the formula of CV square and whatever change in C and V you have to substitute. If you want to calculate the electric field, again use the formula E is equal to V by D. So whatever question asked related to this, accordingly use the formula and follow this method which we have used here and find whatever changes in the capacitor. Now second part, after the supply was disconnected, supply is disconnected. When supply is disconnected, there is no circuit for the flow of charge. Therefore, in case B, you have to take Q is equal to Q naught. No change in charge. Okay. Whenever supply is disconnected, means charge remains constant. And charge remains constant means what happens to voltage? We can just try to calculate. We have V is equal to Q by C. V is equal to Q by C. The first case we have to take a Q naught, V naught is equal to Q naught by C naught is equal or V is equal to Q by C is equal to Q and Q naught are equal. So Q naught divided by K C naught is equal to Q naught by C naught is again V naught. So we have V naught by K. So what happens to the voltage? The voltage is decreased by 1 by K times. And for such questions, this kind of questions, you need to obtain the answer like this. And finally, you have to write your conclusion also. In words, you have to write your conclusions. Here, voltage becomes 1 by K times. Okay, that's about question 9. Now, come to question 10. A 12 picofarad capacitor is connected to 50 volt battery. How much electrostatic energy is stored in the capacitor? Energy E is equal to, or energy, I use the formula U to avoid confusion with electric field. Energy U is equal to half CV square. And in the question C and V are given. So directly you can find the answer. Then question 11. A 600 picofarad capacitor is charged. Okay, capacitor is 600 picofarad to a potential 200 volt. So you can take as C1 as 600 picofarad. So C1 equal to 600 picofarad. Then V1 is equal to 200 volt. It is then disconnected from the supply and is connected to another uncharged capacitor that also 600 picofarad. So C2 is equal to 600 picofarad and it is uncharged capacitor. Being uncharged capacitor, value of V2 will be 0. then how much electrostatic energy is lost in the process. So there are two methods we can use. First, you can calculate initial energy, then you can calculate final energy. They will share the capacity charges equally. So you find the charge in the first capacitor, then take a case that they share the charges, and you can calculate the final energy. Then you can take the difference between initial energy and final energy. But we have already an equation for loss of energy in sharing charges. So loss of energy in sharing charges, okay, is equal to, so the energy loss of energy in sharing charges U is equal to C1 C2 into V1 minus V2 the whole square divided by 2 into C1 plus C2. This formula can be used directly so that we get the answer directly. No need to calculate initial energy, final energy, etc. Loss of energy we can calculate using this formula. When you substitute the values of C1 and C2, it should be in SI unit, not in picofarad, it should be in farad. So you will get the answer directly. Now, next. Sorry. Question 12. A charge of 8 millicoulomb is located at the origin. The diagram. 8 millicoulomb is located at the origin. Here. 8 millicoulomb. Then calculate the work done in taking a small charge, another charge of minus 2 into 10 power minus 9 coulomb from the point 003. 003 means from Z axis to a point 040. That is the final point 040 on y axis. A point R 069. That point is in YZ plane. Okay. Now, you know, here electrostatic force is a conservative force. So work done in moving the charge depends only on initial position and final position. So what do you have to do? Calculate the potential at the point. We can give the, okay, it is already given point P. Potential at the point P we can take. And potential at Q is the final point. So Vp is the initial potential and Vq is the final potential. Then work done we have to calculate. We know work done is potential energy. So initial potential energy UP is equal to Q1 into Vp. And final potential energy UQ is equal to Q1 into VQ. Now, what is the net work done? Net work done W is equal to change in potential energy UQ minus UQ minus UP. UQ minus UP. Then here that is equal to what can be done. So when you substitute the value Q1 is common. And the potential formula, potential due to point charge 1 by 4 pi epsilon naught. Now, this potential is created by the charge 8 millicoulomb, which we can take Q into, what do you get, 1 by R1 minus 1 by R2. How much is R1 and R2? R1 is initial position, initial distance between 8 millicoulomb and point B, that is 3 centimeter, and R2 is the distance between 8 millicoulomb charge at the origin and the point Q, that is 4 centimeter. Substitute the values in SI unit and you can calculate the value of what. Now come to question 30. A cube of side B, diagram you can see there, has a charge Q at each of the vertices. Charge Q is there at each point, each corner. Determine the potential and the electric field due to this charge array at the center of the cube. You have to calculate electric field and potential at the center. You take the case of the center, you can see all charges are positive charges. All of them will apply. The center we can take like this. From all the coordinates, electric field will be applied like this. In this way, from all coordinates. From positive charge, it is radially outwards. Therefore, what is the value of electric field? The electric field will be 0 at the center. So that is the first answer. Electric field is 0 at the center. Now come to the potential. The potential will be added up because potential is a scalar quantity. So then, how can you calculate the potential? Can calculate the potential. There are 8 coordinates, so 8 charges are there. So potential V is equal to 8 into 1 by 4 pi epsilon naught. 8 into 1 by 4 pi epsilon naught Q. All charges are identical. Q divided by R. You will get a potential. And the question will come, how much is R? So you have to see this diagram. The midpoint is here. Okay, first you have to calculate D, the diagonal. B is given. So D you have to calculate first. So D is equal to, I think you will get D is equal to root 2 into B. D is equal to root 2B you will get. Then again we have to see another right angle triangle here in such a way that the base is D, the perpendicular is B height, and the diagonal we have to take. So again use Pythagoras theorem, you will get a diagonal from these opposite coordinates, diagonal between the points A and B. You will get a root 3. AB is equal to root 3B you will get. And the midpoint. The midpoint means what is the value of R there? R is equal to root 3B by 2 is the value of R. So you have to substitute that value in this equation. No other data is given, so only final formula is required. So substitute the value of R, you will get the answer. Now, next, question 14. Two tiny spheres, charges 1.5 microcoulomb, we can take as Q1, 1.5 microcoulomb, and 2.5 microcoulomb, take it as Q2, 2.5 microcoulomb, separated by 30 centimeter, 0.3 meter. Then, these are the data given. Find the potential and electric field. You have to find the potential and electric field. Part A, at the midpoint of the line joining two charges. At the midpoint of the line joining two charges. Okay, so what do you have to do? First case, we need to calculate, diagram is given. This is a diagram for case A. Now potential, how can you calculate potential? Potential is equal to total potential V is equal to V1 plus V2. Potential we can add. So V is equal to V1 plus V2. Substitute the values of V1 and V2. You will get a 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught distance will be 15 centimeter, which we can take as R into 1 by R. Remember, R is equal to 15 centimeter into, you will get a Q1 plus Q2. Both are positive charges. Q1 plus Q2. Substitute all the values in SI unit, you will get the answer. Now, next, come to the total electric field. Electric field, electric field has direction. So, both are positive charges. Electric fields are radially outward. So, here you can see due to 1.5, electric field is from left to right. And due to the charge 2.5, electric field is from right to left. So what do we have to do? We have to find the difference to get the resultant electric field at the point O. Here, definitely distances are equal. So 2.5 microcoulomb will produce a stronger electric field. Therefore, resultant electric field I am going to take as E2 minus E1. E2 minus E1. So that is equal to, again you can substitute the values, use the same formula, electric field due to point charge 1 by 4 pi epsilon naught 1 by R square into Q2 minus Q1. 1 by R square into Q2 minus Q1. You will get the resultant electric field. So we have completed the part A. Now, next, come to the part B. At a point 10 centimeter from this point, this midpoint in a plane normal to the line and passing through the midpoint. So we need to draw the diagram again. Here we can have so here charge Q1, charge Q2, the line passing through the midpoint, this point O, this distance is 0.15 meter, this also 0.15 meter. Then distances from the charges, and this distance is 0.1 meter because it is given 10 centimeter. Okay, now first of all, potential. How to calculate potential? You have to use again Pythagorean theorem so that you can find the length is about around 0.18 meter. You will get here also 0.18. So now potential we can calculate. V is equal to, use the same formula. V is equal to V1 plus V2. V1 plus V2. Use the equation for potential due to point charge. Again, the first formula which we have used, the first part we can use. Only the difference is that you need to take R is equal to 0.18 meter in this case, so that Using the method which we have used in part A, we will find the value of total potential. Now, next, come to the electric field. Electric field directly we can't calculate because electric field is a vector quantity. Okay, so we need to take the directions. So the first field we can give the name E2, field E2. Then next we can have field E1, E1 and E2. Now here what can be done? Here we can complete a parallelogram. Complete the parallelogram. We expect the resultant field will be close to E2 because E2 is strong. So we have to construct the parallelogram in this manner. So the resultant field, and take this total angle theta, and the resultant field will make a direction like this with respect to the distribution of two charges, direction of the resultant field. Okay, so this is the situation. Now, what we have to do? We have to calculate the value of E1, find the value of E1 using the formula 1 by 4 pi epsilon naught Q1 divided by R square. R again you have to take here 0.18 centimeter, sorry 18 meter. Then find the value of E2, electric field produced by charge Q2 we need to calculate. After getting the values of E1 and E2, next step we need to find this angle. This angle will be theta by 2. Theta by 2. Then, how can you find this angle? So you can take one of the trigonometric ratios. For example, suppose you take cos theta by 2. Cos theta by 2 will be 0.1 divided by 0.18 and find the value of theta from this equation. Obtain the value of theta. Using the formula, you need to find the value of theta. Once you get the value of theta, now you can find the resultant electric field E. How do you find resultant electric field E? You have E1 square, cosine rule you have to use, E1 square plus E2 square plus 2 E1 E2 cos theta raised to 1 by 2. So you will get the magnitude of electric field E. The next step, you have to find the direction. So how can you find the directions? Take this angle beta. Angle beta. Then again last year along with this cosine rule you have studied tan beta is equal to, there's a formula for tan beta. Tan beta is equal to E1 sine theta. E1 sine theta divided by E2 plus E1 cos theta. And using this equation, find the value of angle beta. Find the value of angle beta. Now you see this angle is angle beta. Then this angle can be calculated here. How can you calculate this angle? So here this is a right angle triangle. Therefore, that angle will be 90 minus theta by 2. 90 minus theta by 2. Now, find this angle. Say angle phi. How to find angle phi? Find the value of angle phi using exterior angle theorem. So now, see there, you will get the magnitude of resultant electric field at this point, okay, and the direction of electric field with respect to the line joining the charges Q1 and Q2. Okay, so these are quantities you need to calculate for this question 40. Now come to question 50. A spherical conducting shell of inner radius R1 and outer radius R2 has a charge Q. A charge small q is placed at the center of the shell. What is the surface charge density on the inner and the outer surface of the shell? Okay, so we need to consider a shell. Okay, now the shell has inner radius and outer radius are given. Inner radius R1, inner radius R1, outer radius R2, outer radius R2, and shell is given charge Q. Then a charge Q is placed at the center of the shell. Another charge Q is placed at the center of the shell. Charge Q. Then when you place charge Q at the center of the shell, you know here charge minus Q is induced. Charge minus Q. When charge minus Q is induced, actually it is due to the movement of negative charges in the shell towards the inner surface. So naturally what happens? Outer surface charge plus Q will be induced. Charge plus Q. So what is the total charge in the outer surface now? Already it is Q. Now it becomes Q plus Q. So this is the situation. Now, and already have studied when charge is given to a conductor, that charge will be distributed over the surface of the conductor. That is the reason capital Q is distributed over the surface only. Now you are asked to calculate the surface charge densities. Okay, surface charge density. First one we can take sigma 1 for inner surface. That will be minus Q divided by area of the surface 4 pi R1 square. And for the outer surface, sigma 2 is equal to Q plus Q. That's the total charge distributed in the outer surface divided by 4 pi R2 square. These are the answers to part A. Now come to part B is the electric field inside the cavity with no charge, 0, even if the shell is not spherical but has any irregular shape. Okay, so you can take any irregular shaped surface. Whether the electric field inside the cavity is 0 or not, that's the question. So here also, what you can do, you can imagine a Gaussian surface there. Okay, imagine a Gaussian surface. And what is the electric field over the Gaussian surface? Definitely electric field will be 0. What is the reason? Electric field is 0 because there is no charge inside the Gaussian surface. Therefore, we can conclude whatever be the shape of the shell, okay, inside the shell, electric field will be 0. Okay, now come to question 16. Show that the normal component of electric field has a discontinuity from one side of a charged conductor to another given by E2 minus E1 dot n cap is equal to sigma by epsilon naught. So you are asked a conductor. So here, take a conductor. So like this, we can consider a conductor. And you know, for this conductor, electric field inside the conductor is 0. But electric field, you can see electric field is present outward. And electric field again present the opposite direction towards here also from every point. So we take it as this electric field E1 and here electric field E2. And what is the electric field inside here? The value of electric field inside. So there is no electric field inside. Electric field inside the conductor is 0. There is a meaning in the question. It says there is a discontinuity in the conductor. If you take E1, E2, when you move from one side to the other side, inside the conductor there is no electric field. Okay, which means there is a discontinuity. Now we can take E1 is equal to minus sigma divided by 2 epsilon naught n cap. Because according to our diagram, that electric field is acting towards left hand side. Now, the same way E2 we can calculate, E1 and E2 are vectors. E2 is equal to sigma divided by 2 epsilon naught n cap. Now, we need to calculate E2 minus E1. Now, E2 minus E1 is equal to E2 minus E1. E2 minus E1 is equal to, we can substitute the values there so that you will get, when you substitute the values of E2 minus E1, you will get sigma divided by epsilon naught. This become minus or minus plus, sigma divided by epsilon naught n cap, you will get E2 minus E1. Now, both sides of the equation, you take a dot product with the n cap, that is E2 minus E1 E2 minus E1 dot n cap is equal to sigma divided by epsilon naught dot n cap. Sorry, sigma by epsilon naught n cap dot n cap. So it becomes E2 minus E1. E2 minus E1 dot n cap is equal to sigma divided by epsilon naught. N dot n is equal to 1. That's it. So that's the proof of the first part. Okay, now can show that just outside the conductor, electric field is equal to sigma by epsilon naught n cap, just outside the conductor. So when you take just outside the conductor, such a concept when we take, we can first start with this formula. E2 minus E1 is equal to sigma divided by epsilon naught n cap. Okay, now the same conductor we take, but we want to make E1 0. Therefore, we consider the conductor like this, in this way. Okay, so E2 is acting towards here, and being inside the conductor here, value of E1 you can take 0 and use this formula. E1 is 0. When E1 is 0, you will get E2 is equal to, when E1 is 0, E2 is equal to sigma divided by epsilon naught n cap. So you will get electric field is sigma divided by epsilon naught n cap. Then why can't we consider E1 here at the end? So that E1 is supposed to be somewhere. Okay. We will have at this end of the conductor only. Here when you take this edge, we have no other option, even we have to take 0. Whether E1 is present far away from there, infinitely distant away, etc., we need not consider at all. For us, for this edge inside the conductor, E1 is 0, outside E2 is there. So we use that equation. So you will get E2 is equal to sigma divided by epsilon naught n cap. Now, part B show that the tangential component of electric field is continuous from one side of the charged surface to another. Okay, again, carefully we have to see there. We take a conductor and for this particular conductor, so take a conductor like this. Now, in that conductor placed in external electric field, we have seen electric field is acting normally to the surface of the conductor. Okay, there is no tangential conductor, not possible, etc. We have seen. Now, just imagine what will be the situation here. Suppose you take a charge from this point and move the charge around this conductor. You will go to the other side and you will continue to reach here. How much is the work done? You are moving the charge along a closed path in electric field. Work done is 0. So now Just imagine that in such a situation, there is a discontinuity here. Means there is no electric field in this between these two dots. So what happens? You take the charge from here, move around this conductor and reach here. Afterwards, there is no electric field. If you want to move the charge from first point to second point, then you need to perform work. So then what happens? If there is a discontinuity, to move the charge around a closed path, you need to do work. That is against the idea of our conservative force. Therefore, what we have to imagine on the surface, the electric field has no discontinuity. If there is discontinuity, work done to move, already it is mentioned in the question, work done by electric field to move the charge on a closed path is not zero, but we know it is zero. Always work done to move the charge over a closed path in electric field is zero. Therefore, as an implication of this point, we can say there is no discontinuity on the surface of the conductor. Electric field will be continuous. There is no discontinuity here. Okay, so this sentence itself is the answer to the question.